Great. So good afternoon. Thank you guys for coming. I am Michael Solberg. I am what we call a chief field architect at Red Hat. I am based out of Atlanta, Georgia, and I cover the Southeast region. So my job basically is to work with large companies or strategic customers of Red Hat to help them implement a Red Hat set of technologies. Today, I want to talk about Docker, and Docker in the aspect that it underlies a lot of our newer technologies coming out. So OpenShift, RHEL Atomic, RHEL 7, they all have a strong basis for using Docker and working with Docker. And so today's presentation is about Docker in the CI/CD workflow, because I think that's where it makes the most sense to think about Docker. And we'll look at traditional CI/CD workflows and new CI/CD workflows using Docker and compare and contrast a little bit, right? Because I think if you guys heard Joe's talk, did you guys hear Joe's talk earlier about Atomic? So one of the things that he said was, he talked a little bit about the complexity of setting things up in Docker. And I think once you've taken a look at some of the complexity that was in the original pipeline that we already work with, and then you see the lack of complexity in the Docker pipeline, I think the complexity of implementing Docker kind of gets canceled out by the previous complexity. So we'll take a look at that. Hopefully I'll make it look very simple. I have a simple example today that we'll look at. We'll take a Django application and we'll go from source to deployed Docker, and that'll be through the pipeline. So the first thing I want to talk about is CI/CD. This would be a broad overview, and I apologize for the broadness of it, but I think it's important to talk about it in the context of Docker, because I think the use case for Docker is CI/CD. So the main tenets, why do we have continuous integration? Continuous integration is built to solve the problem of, did I just break something when I committed some code? This doesn't necessarily have to be software code, right? So we use CI when we do Puppet class updates as well throughout the infrastructure with some of our customers. If we're doing like OpenStack deployments or something like that, we'll have a set of unit tests that we can run after we deploy systems and configure them. The same is true for software. The idea of writing the test first, implementing the feature, and then ensuring that the test succeeds. These are all the things that we do in CI. So there's kind of three pieces of testing in CI. There's a test before you push. So this is where I'm going to run like a lint test against my particular set of source code. I want to make sure that I'm using two spaces instead of a tab key at my Python, things like that. Make sure that the code compiles, syntax, and then to some extent unit tests as well. This is all stuff that I do on my workstation, right? So there's not really, if you look at like opportunities to use Docker and leverage Docker, there really isn't much Docker there. But when you get into the after the push, you do have some opportunities, right? So traditionally what we'll do is we'll download source code onto a build machine, we'll build it there, and then we'll run our tests there. And what this proves to us is that the code that I'm building isn't just code that I can build on my own workstation, but it's code I can build somewhere out in a further environment. Docker can help us with that reproducibility. We'll take a look at that. And then lastly, the before you deploy. So it's important to be doing integration testing, performance testing. It's one thing for the code to build on a build server and to pass tests on a build server, but it's very different to have the code be deployed into a production environment and have the same performance characteristics that you have in the current running build. So did anybody read Limoncelli's new book, Cloud System Administration? This is a really good book. It's out there. He wrote The Practice of Network and System Administration a while back, and now he has a book around cloud system administration, and he talks a lot about how Agile development, DevOps, some of these things have changed the way that software is deployed. We'll take a look at some of these practices later on. But one of the most important things that he talks about is not only testing functionality, not only doing user acceptance testing, all that, but really being really careful about performance testing, right? So if you're Google, and all of a sudden your search requests take a hair of a second longer, you just at web scale, it can be a dramatic change in either it works or it doesn't work, right? And then the last piece that we want to talk about here a little bit is merge testing, right? So if you've got a team of 25 developers working together, all the code comes in at the same time, you need to make sure that you're passing unit tests throughout all of the developers' code as an assembled whole. This becomes much more important when you're working on open source scale projects. So this is an example pipeline from the OpenStack Nova project, where you have hundreds of commits, right, coming in from hundreds of developers all the time. It's very important that as the code gets merged back to master, we're doing lots and lots of CI on it to make sure that we're passing tests that, this fix over here and that fix over there together don't break things. You see here in the CI pipeline for Nova, code gets moved into a local environment. Then we do branching, so we do feature branches, bug fix branches. We do all of our testing locally to make sure that we haven't broken anything there using DevStack. We push it into Garrett. You've got humans that take a look at it in Garrett, do code audits, code reviews. You also have Jenkins do a code review by trying to build and pass unit tests in Garrett. It passes then again to Jenkins once everyone has approved the change to make sure that all the changes together still have a functional whole, and only then do things get past the gate into the master. So this is kind of the model that I think organizations have successfully deployed in CI over the last, let's say 5-10 years as CI has become really big and become key. This is a pretty typical CI workflow, right? It has the human checks, it has code reviews, it has unit tests, all these things. Now, if you look at the CI workflow, you kind of look here and you say, is there an opportunity for Docker to help out here? Maybe, right? But this workflow works pretty well just using the traditional tooling, and it's something that we've had for a while. So we'll kind of look later. I think the real opportunity for Docker, is in CD. When we talk about that, the continuous delivery, that's where the Docker is really key. So for our example application that we're looking at today, it's the Django polls application. Here is a build script that we run in Jenkins that just does basic testing. I'm going to point out a couple characteristics about the build script, and how this is the one place where I think Docker does make a big difference. So when you're doing builds, at least of Python applications, and somewhat is true for JE apps and other applications as well, you want to do something. In Python, it's using a virtual environment. In Java, you see people kind of having build trees, but you want to make sure that you have kind of a clean room environment where you're pulling requirements in for each of the builds on the build server, right? You don't want to have this project's build affected by someone needing a different version of something over here. So in Python, we solve this problem using virtual environments. And you see the first thing that I do in my Jenkins build script for the Django app is that I create a virtual environment, I install my requirements, I validate and then sync and then test. That's the kind of 3 steps I'm going to use to do testing on my Django app, right? So one thing to think about, and we'll see this when we do Docker, is when I do a Docker deployment of an application, I don't have to use a virtual environment, right? Because I'm running inside of a Linux container. And then another thing that's really nice when I'm doing this with Docker is that here I'm doing a pip install into my virtual environment. Well, how do I know that my production environment is using the same versions of applications that I'm getting in my virtual environment, inside of the unit testing? So that's something to think about as well. So let's talk about CD, because I think that's where Docker makes the largest impact, and I think where we're seeing the strongest adoption of it. So the first thing, and if you saw Joe's talk earlier, we talked about packaging formats. We discussed that a little bit here. Docker kind of obviates the need for packaging formats in one hand, in that we're kind of passing around Docker images and we're not passing around RPMs anymore. But on the other hand, it leverages it too, right? Like when I'm installing code to create the Docker image, I'm still going to use pip, or I'm going to use RPM, or I'm going to use tools like that, jars, wars, ears, tars. So to some extent, the packaging obviated the differences in the languages and the ways. But on the other hand, even though I have a Docker image at the end result, I'm still using my native tooling. So the good news there is that stuff that I've already done doesn't go away when I go to create my Docker image, right? I'm still using my Yum repositories. I'm still doing all these things. But the even better news is that my end result isn't something that has to be deployed differently. So I think that's a huge, huge advantage of Docker and CD. But in the traditional one, we still had ways to do this, right? So you think about the application, we'll look at the steps a little bit, but you take the RPM result out of the build, put it in the Yum repo, pull it down, so on and so forth. The trick here is that every build that I'm doing that succeeds passes through a gate, goes into the repository, and is coming out into the environment for me to test, right? There's no human being picking up a release and sending it out. So for our application, let's look at the traditional actual deployment process. The first thing I might do if I'm building it into an RPM, maybe I've got a package.spec that I'm putting inside of the source code repository. I'm running an RPM build on it, getting a packaged artifact. I'm taking that artifact, pushing it into a repository. But then here's the trick, right? So now I've got that package and it's in the repository. How do I get it out into UAT? Right? Well, now I have to log into all of my UAT servers and I have to do a yum update. Well, how do I roll back the yum update? I mean, you end up in all these traditional, complications around the actual pushing and the pulling down, and then you have to restart services. And this process is different for every different type of artifact, right? So this works for RPMs, but it doesn't work for ears. It doesn't work for wars or jars. And so what we find is we find people packaging jars as RPMs, or you package wars as RPMs, or you take Python packages, you turn them into RPMs, so that you have a consistent way to do updates and rollbacks. But there was a lot of engineering that's gone into these pipelines, right, to create that kind of ability to do that. And then you have a lot of people in a lot of environments that instead of doing this, right, they just do a kickstart. They just grab 3 virtual machines and kickstart them, right? They might go into OpenStack and do some kickstarts, or they might, bare metal kickstart boxes to create, this process of deploying. So it's kind of long and painful and a little bit complex. Lastly, let's look at the rollout. So let's say we get through all the testing. We've done our continuous integration testing. We've done our continuous delivery. The build is out into the UAT environment. And in this diagram, it's a little small, but on the left side, I've got build 32 running on 2 machines. I have build 30 running on 4 over here. There's a load balancer sitting in front. The kind of last process, I have a human user looking at build 32 running in that testing environment, or maybe I switch over a subset of my live users in production to that testing environment. And assuming as I'm watching the logs that there are no failures, no 404s or 500s, or if I've got a human user, they're seeing the things that they want to see in the application. Then I slowly start updating, pull a production box out of the rotation of the load balancer. I do a yum update on it. I restart services and I bring it back into the load balancer, right? And I start, one by one scooting across and using the load balancer to bring in boxes up to build 32 instead of build 30. And this works, right? This is a tried and true way to do it. And you can do this without Docker, right? And we do this today. But let's take a look at Docker, and let's run through the same pipeline with Docker, see how this is different, right? So like we said, the main advantages of Docker are the consistent delivery format. Another one that we didn't talk about, consistent packaging definition, right? So everything is stored in the Dockerfile. I don't have specs. I don't have Maven build.xmls or POMs or whatever, right? I have a Dockerfile, and everyone can learn how to write a Dockerfile. It's just basically shell scripts. And so really simple, and I check it into my code repository. We'll see how that works. And then the last piece that's really important with Docker that we don't talk about a lot is that Docker has built-in deployment infrastructure. Right? Out of the box, Docker has a way for me to take some code, turn it into an image, push it somewhere, and then have it immediately be available to my environment to pull out. It kind of has like a built-in Yum repository or a built-in Python package index or things like that, right? And it's across the board, right? So my Java apps, my Python apps, all of that can be in the same registry. Coming back to the idea of formats, I just wanted to kind of put up here, I think this is interesting, the way that the formats differ in the traditional and the Docker deployment models. You think about the bottom half of this, you have your kernel, your system libraries, and your application libraries. These typically come from your distribution vendor, right? So this is Red Hat providing this or CentOS providing this. And it's going to be in the operating system format. So it'll be RPM or apt, right? And then above that, your actual container is either going to come from a vendor like Red Hat. It might be JBoss EAP, or it might come from EPL, or it might be something that you roll in-house, right? That is where we typically start to see the package formats diverge. So a Python container might be installed via pip. You might have a Java container that's downloaded as a zip file. You might have Ruby, however, the Ruby guys do it with gems, right? So you start to see that divergence there at the container level, and then at the very top, you typically see developers. Yes, question? That's absolutely right. Yeah, I'm talking about the layers of the application stack for a Django application. Absolutely right. So you think about at the top, the developer wants to take his source code and drop it in a container, right? And so that'll take a different format, right? It might be a get checkout, or it might be a tarball or something like that that gets dropped into the container. Organizationally, this has evolved because different people are doing these different tasks, right? So your Linux distributor is picking a package format to give you the bottom 3 pieces of the stack to, right? So Red Hat decided RPM today and whatever it is tomorrow. I forget what it is, but and then up higher, you've got an operations engineering team that's decided, hey, everyone in my company is going to use Django 1.6, and it's going to be our build of Django 1.6, and it's either going to be an RPM or a pip or whatever, right? And then at the top layer, the developer is kind of making the decision as far as, or at least the developer's architecture team is making the decision as how they're going to deliver code artifacts. And that's why the segmentation in formats has seemed to be okay up to this point. But as these roles start to merge, right, the container typically comes from an engineering team, but let's say it could be an operational engineering team, so I can get DevOps into this talk. But let's say as those roles start to merge and you've got application teams that are interested in working on engineering, or you've got engineering teams that are going to write some applications, the disparate package formats start to become a problem, right? Because a domain expert in writing RPM spec files is not going to be a domain expert in writing Maven files. And so having consistent package format with Docker, having a Dockerfile format that everyone can rely on, enables some transition and crossover between the different roles in the organization. So you kind of look at, we had the applications traditionally. This is a Docker application stack. On here at the bottom, I have RHEL 7 Atomic. We talked about Atomic in Joe's talk earlier today. Atomic is Red Hat's Docker running operating system. It's custom tailored for running Docker containers. And it's distributed as a binary image, right? And you roll forward and you roll back binary images just like you do with Docker images. So that's provided by the distributor. Now, the distributor will also provide you with a layer above to do the system libraries. So in this particular example, I've got a RHEL 7 Atomic kernel. I'm running a RHEL 6 system library on top of that with a Red Hat provided RHEL 6 image. And then above that, Red Hat provides images for certain languages in certain operating systems as a part of our OpenShift offering. This one could also be created in-house. If you have an engineering team that wants to create your own Python distribution on top of RHEL 6. Then I have a Docker image on the top that's a Django. So this maybe is a centralized engineering organization. So my Django container looks like this. It's version 1.6.1. Here's my image. And then lastly, the developer who's writing the polls application, his Dockerfile pulls the Django 6 Dockerfile, which creates this heredity. So one of the things that's neat about this, right, is you might have a developer writing a Docker file for the container because they're working in the same technology space, but you might also use the exact same organizational structure that you have today, right, where you have a container engineering group that's got standards around JBoss or Rails or whatever, and wants to maintain a single container image that all the different development teams use. Because everybody's speaking the same language, it doesn't matter so much, right? You can really cross over back and forth. So we looked before at a deploy process in the traditional sense, and we'll look at this now, in a minute here with the polls application. But the deployment process is radically different with Docker, and this is where things really start to change, right? So instead of packaging up my source code, I just drop it into the Docker image using the Dockerfile. Right? So I use this, add.webAppsPolls. I take my code and I drop it into the Docker image, and then I build the image, right? So the first 2 steps here, totally the same regardless of what kind of source code I'm using, right? Doesn't matter. Could be Java, could be Python, could be Ruby. And then the result is a Docker image that I can then take and deploy. So I tag it, and then I push it, and it's out in the registry. There's like 3 or 4 commands, right? And I already have my source code deployed in a way that my UAT environment can go ahead and pull it down. And then when it pulls it down, this is where things are really radically different, right? So if you think about the traditional deployment model where I'm doing a rollout, I've got the build 32 on the left, I got build 30 on the right, I'm rolling machines back and forth. With Docker, since it's containers, I can simultaneously run both builds on all of the machines in my production environment. Right? I can run one build on port 8080, I can run the next build on port 8081, the next build on port 8082. And instead of taking machines in and out of my load balancer pools, what I'm doing instead is I'm just changing the ports. Right? So let's say that everyone's working great on port 8080, then I can move the load balancer to that port. Everyone starts to work really well on 8081, I move the load balancer to that port. Maybe I found a problem, 5 minutes, 10 minutes into my deployment on port 8081, no problem. I just point the load balancer back to 8080 and I've immediately rolled back my environment. Right, and that is the real difference, right? That's why web scale companies are adopting the container format and the container deployment model, because it's so much radically different when I go to actually do the rollout and the rollback. So it's been a long time since I've done a production rollout of code, but I remember sitting for hours with operations teams as we kickstarted boxes, trying to get back or trying to go forward. With the new model, it's just seconds, right? Like I'm just moving the stream of requests in and out. So let's actually go to the demo. So first of all, I'm going to start with the Jenkins dashboard. So I'm using Jenkins, which that means you're doing CI, right? You guys ever been to there's the joke that everyone talks about where you're like, hey, do you do CI? And they're, oh yeah, I'll use Jenkins. And then they actually aren't doing CI, but it's maybe not a funny joke. Anyway, here's well, continuous integration, I define it as taking the source code, running tests on it, getting feedback. So it's all about feedback. It's all about getting the feedback before I commit to make sure, hey, system, tell me, did I write a mistake? Getting feedback after the commit, did my test pass? Then getting feedback as it goes to build. And it's feedback at all these different levels that makes it continuously integrated. And then also pulling all the commits together. That's the integration part, right? So my commit, Bob's commit together, let's get feedback. Yes? The previous question was, how do you define continuous integration if it's not Jenkins, right? Because I think that's the joke is someone asks, hey, what's CI? And you say, oh, it's Jenkins. But
I did to my company, but
yeah.
Based on what you're saying, we're pretty close to.
You probably are doing it right, and that's why the joke is interesting, right? Because it's hard to do CI without a tool like Jenkins. Most people that use Jenkins are doing CI, but so. And actually, all of that said, this particular example that I have up here does not provide feedback except for the web form, so I'm probably not actually really doing CI here. So that kind of brings it all full circle. But let's talk about what I have defined here. So I have CI demo. This is the project that we're going to be looking at today. We're going to be deploying, modifying the source code. Then I have 2 steps. I have a package step. So this takes the CI demo code and actually creates a Python archive that we could then deploy in a rather cumbersome way using the traditional pipeline. And then I have a Docker build as well, right? So if the code completes the first step and all the tests pass and everything is good, and I do my integration testing on the source code there, CI demo, then it moves into these 2 subsequent builds. And I have one that does Docker packaging and one that creates the Python package. And the Docker packaging step also deploys the new Docker image to my Docker registry. And what we'll see here is once it's deployed to the registry, I can pull it down on a RHEL atomic host and fire it up and start it. And then also I'm building my Docker images from CI. And that's probably a discussion for a longer discussion. But since each Docker image builds on each other, let's say I have my RHEL 6 Docker image, and then I have my Django image, and then I have my actual application image. As we move through the application lifecycle of each one, I need to rebuild my images, right? So if I get some updates from Red Hat in RHEL 6, I need to update my RHEL 6 image. Then I need to update all of the images that come beneath that. And so what we do is we use a tool like Jenkins to set up these build workflows where I can build one image after another one gets updated after another one, and then automatically deploy them out to my environment so I can switch back and forth, right? And then let's just real quickly look at the actual projects. So now I'm looking at the CI demo project. We'll just look at the build script. It's the one that we had defined before down here, right? So I'm creating a virtual environment. I'm entering into the virtual environment, installing my requirements, and then I'm running the basic tests, right? Validate, syncdb, and then unit test. One thing to note here is I do create the virtual environment in this step. But when we look at the Docker build, that does not run in a virtual environment. It just runs natively in the container. And the container provides the virtual environment isolation for us. And then let's look at the Docker project and look at its build script real quick. We scroll down. So there's a lot of talk about Docker being really complicated and hard to understand and complex. My build scripts are like 2 lines, right? This is really simple. Now, it took a lot of conceptual understanding to figure out how to set it all up and I had to create a build flow to create my Docker images, but going from source code to Docker image, like I said, it's 2 lines, right? The first 2 lines I have Docker build and Docker tag. That takes my code, it builds a Docker image, and it tags it, so I know what version. I tag it with the build number from Jenkins. And then the next script actually pushes it out to the registry. So I tag it again to tell it which registry to send it to, and then I do a doc push. And with that, my code is deployed, right? So, you know, I think we talk a lot about the barrier to adoption of Docker and how difficult it is for organizations to adopt new workflows and things like that. But when you actually get down to it, like I said, we're talking about 2 lines of code. And that's a very simple example, don't get me wrong. But on the other hand, it is not complex to get this thing going. Let's take a look real quick at my Docker files as well, so we can get a feel for that. And like I said, they're checked in with the code, right? So this is the source code for the polls application. And we have the requirements.txt that you'd expect, the setup.py that you'd expect, but let's just take a quick look at the Docker file. Once again, there's really not a lot to it, right? So basically, I'm doing the same thing that I would do in a virtual environment. I'm creating a code directory, I'm moving into that directory. Then I'm using the same requirements.txt that I use with the pip inside of the virtual environments to install my requirements. And I copy my code in, and that's it. Right, and now the image had to be prepared. So you see at the top, I say from, you know, RHEL Python 2.6. And that's a specially prepared image that has Python pip installed from EPEL. But that's really it. You know, so we're talking about maybe 5 lines in a Docker file to get this thing going. So let's take a look at what it actually does. Let's make a change or 2. So first thing here is I'll edit the default index. Instead of hello world, I'll have it say hello self. There we go. I'm going to add my code here. Then I'm going to commit it. And now on push, I have a get hook that is going to tell Jenkins that there's updated code. You see that down here. It says it's scheduled CI demo. Now, if we go to the Jenkins dashboard, you'll see that the first thing it's going to do is CI. So it'll do my actual integration testing, which it's already completed. And then after it's done with the CI, it starts to do the CD, right? So it's delivering. So it's creating the traditional package, but more importantly, it's running the Docker build. And so the Docker build and the Docker push are happening now. We can actually watch the Docker output. Here it is. So you can see it's running through the steps that I had outlined in the Docker file there. The last thing it's doing is adding my code. The way that Docker images work, each time you run a consecutive change via Dockerfile on the image, it creates a new layer, right? So it can cache layers, it can pull layers back and forth. And you see down here at the bottom, right, that most of the layers in this image have already been pushed. So it's only pushing the change, right? So it's very intelligent about the way it does it. It speeds up the process a lot. And then it allows you, we'll take a look at it as well, to do some inheritance, right? So I can have one RHEL 6 image for my organization. I can have a RHEL 6 Python image for my organization. And everything is really tight, right? So small space requirements, small memory footprints. And that's what allows me to run multiple copies of the same application on the same host. So it looks like we're pushed. Now I'm going to run, log into an atomic host real quick. From the right directory. Let's see here. So I'm going to pull, actually I don't even have to pull, what did I do? So the image that we built was called polls. My Docker registry that I pushed to is called Solberg Docker Builder. And it's running on port 5000. So I'm going to pull the latest image that we just built onto my atomic host. And you see it's got, you know, cache layers, so the pull happens very quick. It's like a, I guess if you look, it's a rather large image, 842 megabytes, right? But because of the layers, it knows only to pull the last little bit, so it happens quicker. And then we'll run the image, right? Now, I have two opportunities to specify a port number here. So I can specify the port number when I run manage.py. I'm going to assign it to 8080. But the real magic of Docker here is you see the -p argument here, where I'm going to map a port inside of the container to a port outside of the container. Right? So in this example, I'm going to run port 8080 and port 8080. But I could change that. I could say, hey, port 8080 inside of my Docker container, let's map that to 8081 outside if I'm concurrently routing. And that's what allows me to move the load balancer back and forth. But we'll just start this up. And then once we've started it, we should be able to curl that and get the updated string. I have to wait a minute. I think it's moving 800 megabytes into memory or something. It's also running on an OpenStack cloud, so. There we go. Hello, self. So at this point, I can take a load balancer, point it at 8080. I could do my testing there, assuming everything passes, or assuming that if I'm actually continuously delivering to production, assuming that I'm watching the logs and I'm not noticing a usage pattern or a performance change as users move on to that port, I can start to drain sessions off of port 8079 or port 8081, right? So that's the presentation. What questions do we have about the workflow that we demonstrated today? Are you guys using this? People that were using Docker are using a similar workflow right now to do the delivery? And do you run concurrent versions on the same host, or do you spread them out? And are you doing any, so you do both, okay. And then do you use any orchestration tools like Kubernetes?
I'm not plugged into that.
You're not familiar. So, okay. So one of the interesting things, so this example is obviously very simplistic, right? I'm running a single container image. I think something that's interesting that comes up is what happens when you have dependent containers, right? So I might have HA proxy running in a container and it needs to talk to Tomcat in a container or something like that, right? And so that's when we want to move a step up the chain and we do what we call container orchestration. And that's where a tool like Kubernetes comes in, right? I can take a set of images, I can run them concurrently inside of what we call a pod in Kubernetes. And then I can manage pod deployments instead of just managing container deployments. That's the strategy that we're using in OpenShift version 3 as well. We use Kubernetes under the covers. There's some customers as well that have adopted Mesos. It's another technology. So Red Hat's kind of looking at the field. We want to make sure that we're being open. And so we're trying to develop a pod definition language that could be used outside of just Kubernetes and could go to Mesos or something like that as well. So I think that's where the magic happens. Yes, question?
Registry there have authentication encryption on it?
No, this registry is insecure. The question was, does the registry have authentication on it? No, I've just set up a simple insecure registry. It's worth noting that obviously you can set up with X509 authentication. And should work. That's the correct way to do it. But the other thing that's interesting too as well is Red Hat adopts Docker throughout our product set, is that we've included a Docker registry in our satellite product. So if anyone's used the Red Hat satellite product for systems management, RPM rollouts, and package management, things like that, the latest version 6.1 includes a Docker registry that you can push and pull to. That's managed, with a graphical user environment, inherits, ACLs from your, enterprise directory service and things like that. So it's all coming together, right? OpenShift version 3 also includes a Docker registry, and we handle setting up certificates between the brokers and the nodes as well there. You can use a self-signed cert, or you can use a corporate certificate as well, if you have one that your organization trusts in OpenShift version 3. So other questions about the build flow? Any other questions about Docker in general? Is everyone's bought in now? We're all going to go home and Docker everything? Yes, question?
Can you explain local development with Docker, how it's developed about putting together Docker image?
Sure. So the question was how would we do local development with Docker? That's a great question. So if you are using obviously using Red Hat Enterprise Linux 7 on your desktop, no problem, right? Docker's included in RHEL 7.1, so you can use that. If you're not, we were talking a little bit about Docker on the Mac. I think Docker is widely adopted throughout a lot of platforms these days. And so, you know, what's that?
That's a VM office.
In a virtual machine. Yeah, so absolutely you could run Linux in a virtual machine. People, is it, Docker's only runs on Linux?
Yes. Yeah, they're talking about it.
It's interesting, yeah. Can you run Docker and Vagrant on a Mac?
But it actually has some support for it.
Yeah.
There's actually a very thin VM image called boot to Docker, which essentially runs Docker in a very thin Linux VM.
Gotcha.
It's just a very small.
So boot to Docker. So I'm in a disadvantage. So I've only used Linux. So everything just works for me. But if you don't use Linux, then maybe you have to do that. But so you know, for example, when I was developing this, I wrote my Dockerfile on my desktop, and I created Docker images using that, and then made sure that that worked. Docker build, and then locally have the Docker image work, and then discard it. And then I check my Dockerfile into source, and then I let the build system create the Docker image that actually gets pushed out. So I think that's the right way to do it. Yeah, question?
Have you done any of this similar kind of stuff with alternatives like LXC or Rocket?
Yeah, so the question was about alternatives like LXC and Rocket. So that's a great question. So I have not used Rocket, and I think I've read press about Rocket, but I don't really understand the difference. Is it very different? I don't know that it's all that different. But LXC is important and interesting, right? So in each successive version of Red Hat Enterprise Linux, 5, 6, and 7, we've had various strategies that we've used to containerize applications. And it started really with RHEL 5 when the release of the NUMA architectures, where we had a lot of customers coming to us with performance issues as we were doing context switching between memory zones in a NUMA box. And so one of the things that we've worked a lot with on those customers, it's almost been, I guess, 7 or 8 years or something at this point, is finding ways to constrain applications first to NUMA zones so that we can reduce the context switching and the performance penalty there. And so we used, I don't even remember what we used, CPU set or something like that in, it was NUMA control or something like that in RHEL 5. I don't know, it's been a long time. But then with RHEL 6, we used C groups, right? So C groups were something that allows you basically to label processes inside of the kernel and then apply constraints. So in RHEL 6, we had full support for CPU sets. And with that, you could take processes and constrain them into memory regions, or you can constrain them to devices, or you say, hey, you can only use so much memory, or you get this priority, things like that. And so we did a lot of work with customers in the RHEL 6 timeframe where you had workloads that needed constraints. So I've got to run database concurrently with an application server on a physical machine on bare metal. I want to put this guy over here and that guy over there. So we started using C groups for that. We also included LXC in RHEL 6. So LXC uses C groups to provide the constraint. So does Docker, right? Because Docker uses LXC, uses C groups. And so I think that, you know, it's been a progression. I think the thing that, and LXC was fully supported in RHEL 6, fully supported in RHEL 7. The thing that is really different in RHEL 7 underlying everything is that LXC, Docker, and then even just process grouping is all run out of systemd. And systemd has the ability to apply C groups at any level of the chain and to kind of divvy up system resources there. So, you know, the thing that we've kind of gone through today about Docker that I think is interesting is the image format, the ability to do, and that's what directly impacts CI/CD. But the performance implications, all of that can be achieved outside of Docker using LXC or just with C groups, right? So the problem becomes, yes, you can run it out of systemd, yeah. So the question is, you know, how do I then solve that virtual environment problem that I'm solving with Docker inside of my C groups? And I think where we've all kind of gotten to is, well, Docker's fine. You know, but I'll take both. I'll take the image thing, and then I'll also use it to do the process constraints. Which, you know, there certainly are environments where we're seeing adoption of LXC just as LXC. There are some advantages. Like, let's say I want to run, I want to put a bunch of different web servers on different IP addresses. but I want them all to use exactly the same code, and I want to be able to update that via RPM. A perfect LXC use case, right? But if I'm actually doing application development and I've got 17 versions of an app that I want concurrently running, that's Docker, solves that problem for me perfectly. It's very difficult to set that up in trees in LXC containers. Question?
More of a comment. So I'm not exactly sure when this change happened, but at some point, Docker changed the default from being based on LXC to create their own library called the container.
Okay. Oh, perfect. So there was a clarification that Docker does not currently use LXC by default anymore. Yeah.
They both still all use the same code.
Sure, they use C groups, yeah, under the covers, right? But the interface to it is the main implication might be through libvirt, right? So we have a libvirt API layer that we can use with LXC containers, and maybe that's no longer applicable to Docker containers.
Well,
Maybe
LXC itself has one of its components, I believe, is a user space library.
Gotcha.
And I think,
So there is, yes. So there's an LXC user space library available on some platforms, but on the Red Hat platforms, we use the libvirt commands to be able to modify LXC containers. So it's all done through Virsh and Virt Manager and OpenStack. You kind of know things like that, talking to libvirt, firing up LXC containers.
they make libvirt LXC library. So,
Exactly, yeah. It has its own implementation of the LXC library, as shipped by Red Hat, yeah.
well, now like you said, now Docker.
Yeah. Perfect. Thanks for the clarification there.
Yeah, I don't know what the details are on that. I remember reading that recently when I was in because I read early on about how Docker had started on LXC.
Yeah, I know an early version of Docker that I used. Absolutely, you could also modify it via the LXC libvirt interface as well.
I think the naming is confusing because there's Linux containers that sometimes can mean what's in the kernel as well as LXC. But then LXC could just be the user space part. So the naming is confusing. I think that's the issue there.
Yeah, I think the other thing it's confusing, right, is we containers is a strategy on Linux. And so we might talk about application sandboxing using SELinux as a container strategy on Linux, totally separate. And now that's privilege isolation, right? And so that's a part of Doc, right? We wrap it in SELinux, as opposed to the performance kind of constraints, which we would implement via C groups. Putting them together, you end up with another technology in LXC or in Docker or in KVM, right? Because at some point, all of this is just a large spectrum of how much am I containing, and there's that line between are we sharing a kernel or not? And the minute we're not sharing a kernel, then you're using all the same subsystems, but you're running in a KVM virtual machine.
But when you say Linux containers, usually that means
yeah, absolutely. So yeah, the Linux containers are normally what you would think of as LXC, at least in my brain, yeah, which is C groups and SELinux, yeah. And then the networking is different, right? So LXC containers may use libvirt networking, whereas Docker maybe has its own. In OpenShift version 3, I think we're going to be leveraging Open vSwitch at some point down the line. So we'll have SDN layers inside of the Kubernetes controlled Docker containers. So it can be a whole lot of different things, right? And even a Docker container running on this particular environment may not look anything like another one if it's orchestrated differently with Mesos or something like that, right? So it becomes a big wash, right? There's a large technology wash right now. Yeah. Yes, question.
Patterns, or do you have any best practices for doing config management with containers? Like what happens when once you build your image, but then you have some environment-specific data that needs to live within that container, such as how to connect to a particular database. Things like that.
So the question was about best practices around configuration management inside of the container. So that's a great question. So there are two approaches. So the first approach, I pass environment variables into the container. And both of these, there's a doc on our knowledge base, by the way, that is a best practices for creating Docker images on Red Hat Enterprise Linux. It has some of this information. But most of that in the atomic space is going to be focused around the environment variables and being able to pass things into the Docker image. What we're doing in the PaaS space with OpenShift version 3, however, is we're leveraging etcd. And so what you do is you kind of push configuration management into the key value store that's distributed via etcd. And then as Docker images come up inside the Kubernetes pod, they can reach out to etcd, get the information and then configure themselves that way. So there's two approaches, right? So the first would be, as I run the image, I'm passing information into it, and then the other one is an already running image, reaching out to etcd and getting information that way. Yeah. But everyone's writing stateless services anyway, right, that don't actually need configuration. That's the joke, right? You know. And then the other question, the next follow-on question, right, is, well, how do I run Puppet inside of a container, right? So, which is funny if you ever tried to do it. But, great questions. Any other questions? That's good. Well, I hope this was a good discussion. Like I said, it's high level, right? But I think it gives us a good framework to think about what's different and why it's good that things are different. So thank you for coming this afternoon, and everyone have a safe travel back. Yeah.
Citrix Zen Server gives you everything you need to integrate, manage, and automate a virtual, all on an enterprise-class, cloud-proven virtual platform, and at 1/3 of the cost of other solutions. But why even bother with virtualizing your server infrastructure in the first place? Well, let's say you have a traditional one-server-to-one application architecture, but you're running out of resources and performance is suffering. Once you order new server hardware, you'll wait for delivery, configure it, install your business application, stage and test the server, and finally, add it to your production farm. If you've been through this process before, you know it can take weeks or even months. You also know it's a manually intensive process that will burden your team every time you outgrow your current setup. With a virtual server solution, you could accomplish all of that in less than half a day. Server virtualization software separates the OS and application from the underlying server hardware. And with multiple virtual machines on a single server, you can use each of them to run different OSs and applications. This makes it possible to move your virtual machines from one piece of hardware to another whenever you want, to maximize utilization, simplify maintenance, or recover from a hardware failure, and without slowing down your applications or users. Clearly, server virtualization provides big benefits, and Citrix Zen Server provides even more. Since it's built on an open platform, Zen Server plays well with your existing hardware, storage systems, and IT management software, as well as with the industry's leading cloud service providers. Best of all, you can get started by downloading a fully functional, production-ready version of Zen Server for free. After a 10-minute installation process, you'll see how easy it is to start virtualizing your workloads and automating your IT management processes. And when you're ready for a richer set of management tools, just upgrade to one of the premium editions of Zen Server. So whether you're interested in virtualizing servers for the first time, expanding your server virtualization footprint, or moving server workloads to the cloud, download and install Zen Server today and see how it can help you simplify your IT environment. Citrix Zen Server. Do more. Don't spend more.
Your customers rely on your website or application. If it's slow or non-responsive, it infuriates your users and costs you money. Keeping your business-critical systems humming along requires insight into what they're doing. Your system metrics tell stories that can reveal performance bottlenecks, resource limitations, and other problems. But how do you keep an eye on all of your system's performance metrics in real time and record this data for later analysis? Enter Longview, the new way to see what's really going on under the hood. The Longview Dashboard lets you visualize the status of all your systems, providing you with a bird's eye view of your entire fleet. You can sort by CPU, memory, swap, processes load, and network usage. Click a specific system to access its individual dashboard, then click and drag to zoom in on choke points and get more detail. Comprehensive network data, including inbound and outbound traffic, is available on the Network tab, and disk writes and free space on the Disks tab, while the Process Explorer displays usage statistics for individual processes. The System Info tab shows listening services, active connections, and available updates. Adding Longview to a system is easy. Just click the button, copy the one-line installation command, then run the command on your Linux system to complete the process. The agent will begin collecting data and sending it to Longview. Then the graphs start rolling. Use Longview to gain visibility into your servers, so when your website or app heats up, it stays up.